but this is a talk about the project Active-Flux scheme third order, high order scheme. And this is funded by NASA in collaboration with the University of Michigan. And my part is to develop this Active-Flux third order scheme for diffusion. In this talk, I'll talk about more on the extension to Advection Diffusion. But actually, this is a talk about the universal idea. You already have it. This is an idea that can be found in any inspirational books of speeches or any folklore in every culture. This is a general idea that you already have everything you want. You want happiness, you have it. If you want a job, you already have it. And the money, you want money, you already have it. You just don't realize that you already have it. So the issue is always just how to manifest what you already have. Like I don't have a pointer now, I need a pointer. But if I look around, yes, here is a pointer. I already have it. The important thing here is that why I looked around, because I believe it. I believe I already have it. That's why I look for and I find it. And this is very important. And the first step is to believe it. You have to believe it, and otherwise you won't get it. And this is true in CFD, and that's exactly what I'm going to talk about. So this was supposed to be a summer talk, but it's almost the end of summer. I'm going to talk about implicit Active-Flux. What is Active-Flux scheme? Active-Flux scheme is a third order scheme, but it can be extended to higher order. The idea goes back to 1977, found to use scheme 5. And decades later, the Amon and Rowe, they took this 1D scheme to multi-dimensional unstructured units. Basic idea is to carry in this one-dimensional computational cell. We carry cell average for the solution, and also the solution values at the face. So we have 3 degrees of freedom within each cell. We can construct quadratic polynomial. And this is the basis for third order accuracy. So this is a finite volume type scheme, but it has, at the face, we have solution values or flux. So these 3 degrees of freedom must evolve independently. So in addition to the finite volume scheme for the cell average, we need to develop a scheme for a face active flux or active solution value. And we focus on implicit time stepping because my part is the focus is the diffusion problem, the NIA CFD. It's good to have implicit time stepping. And so discretized time derivative by some implicit scheme like BDF. So we have discretized time derivative here. And we have to solve this whole system. It's an implicit scheme, so you have to solve the globally coupled system over each physical time step. But typically we take this time derivative to the right-hand side to add it to the source step to define a new source step. So at every physical time step we have to solve this steady problem. And this steady problem can be solved with a pseudo-time derivative. So we have pseudo-time evolution. And if we apply some explicit time stepping in the pseudo-time, we will have a dual time stepping algorithm. But you don't have to keep this pseudo-time. You can simply drop after you discretize and directly solve the global coupled system. So we focus on steady solver. But I will show results for unsteady problems. So advection. This is basically comes from this value's original scheme. But here's advection equation. Simply linear advection. So the flux is some constant A times solution U. So here's this is a finite volume discretization, very straightforward. You just integrate this in space-time. And at the interface, you need to define the flux. And the flux is computed by using trapezoid rule. So the previous time level and pseudo-time level K, you have flux. And then you need to compute this next time level of flux. This is where we need an evolution equation for the flux or the solution. So updated face value is needed. So how to compute this face value? This is very straightforward and natural for linear advection. You trace that. This is the next time level k plus 1, and here's the previous time level k. And you simply trace back the characteristic and find the solution from the previous time level. And you do this at every phase, and you get the next the solution at the next time level, and you compute this flux because it's just A times U. So I denote this operator, just trace back, denoted by A, stands for advection. So this is a complete algorithm in one dimension. And in multi-dimension, I'm not going to talk about multi-dimension, but in multi-dimension, this is where the multi-dimensional upping comes in. You can do without relying on this one-dimensional characteristic. You can take into account multi-dimensional domain of dependence. But that's for details. You can look at this A-row paper. So diffusion. For diffusion, now there is no characteristics. So how to compute the phase value is a question. But we have already developed diffusion scheme based on a hyperbolic formulation, because we are only interested in the steady state and pseudo-steady state. We can solve, instead of diffusion equation, we can solve this hyperbolic representation of the diffusion. As you can see, in the steady state, these time derivatives on the left will vanish, and you achieve PP will be equal to UX, which means we recover the diffusion term, the second derivative here, in the steady state. And this is true for any t. Here's the coefficient. This is called relaxation time. But this can be any non-zero constant. And we have already determined this relaxation time to optimize the fast convergence, fast steady convergence. And so this is order 1. There's no stiffness involved here. This is just a hyperbolic system with source stem. And this hyperbolic diffusion system describes a wave, isotropic wave. A wave traveling to the left and right at the same speed. And so now we have characteristics to trace them. But I'd like to point out that this system is hyperbolic in the pseudo-time. But in space, this is simply elliptic. Because in the pseudo-steady state, this is completely equivalent to the original diffusion equation. So active flux for diffusion, the set average update is just a finite volume with source down. And we need to compute this flux at the next time level. And we trace back now 2 characteristics. So we can apply exactly the same algorithm to each characteristic variables. Let me show you a little bit more details here. So this is the characteristic equations for hyperbolic system. The characteristic variables W1 and W2, they are linear combination of U and gradient P, 2 variables. So, and there are 2 wave speed associated with it. So we trace back, actually we integrate the characteristic equation along each characteristics. And then we obtain these equations. So without source down, this is just tracing back to the right and to the left. And these are the source term effects that need to be taken into account. So phase value U and P obtained by solving this 2x2 linear system. Because W1 is just LP plus U. L is a constant, 1/2π. And W2 is LP minus U. So it's very easy to solve. And the resulting expression, yeah.
You're going back along the characteristic, but don't you need at k plus 1 level?
Yes. Here.
Why you're going back?
Because this solution is convected and reach here. So to find solution here, you can just go back. You find the place where it comes from. Okay. But now there are 2 characteristics. So, okay. So if we solve this 2x2 linear system, we get this expression, these expressions. It looks a little bit complicated, but it is quite straightforward. And now we express this whole operator by diffusion. So given solution value U and P at time level k, this operator finds the solution value UP at next time at the face by solving these characteristic equations. And third order accuracy demonstrated for U and P. This is done last year already. So diffusion scheme is, I know it works.
What's the definition of the source term?
It can be, S1 can be anything. Like I said, an unsteady time derivative or any source term, or some force term. But S2 is this guy, P over T. This hyperbolic formulation has a source term. So that will be S2. Okay. So S1 and S2. But you can have any source term here. And the same algorithm applies. You just plug in S1 and S2 here. Now, the advection diffusion. So once you have advection scheme and diffusion scheme, it's just you need to combine them together to solve advection diffusion problem, right? In many cases, it can be straightforward. However, for this Active-Flux scheme, it is not. And how can we combine advection and diffusion schemes? This is a big question for this type of scheme. The problem is, okay, let me show you. Let me explain why this is difficult. So this is Active-Flux scheme for advection diffusion. So flux has now advective term and diffusion, hyperbolic diffusion flux. So the set average update is this is straightforward, yes. However, at the face, now we have two different characteristic solves. One is advection. This gives tracing back. This gives solution value at the face, k plus 1. And we have diffusion solver also. And this also gives solution value at the face. So which one should I use? I tried averaging. It doesn't work. If I average these two and then compute this flux, I get only first order accuracy. And the reason, I think, because this whole algorithm does not preserve quadratic exact solution. And if you average, it doesn't. So it has to, the whole algorithm needs to preserve quadratic exact solution to achieve third order accuracy. So this is a difficult problem. And I tried operator splitting, like the strength splitting, right? This one and after this one with half time and this one again. And it didn't work. I still don't know why it didn't work. It may be a bug, but I couldn't find it. And there was some time constraint also. But I tried hard and tried harder. And still, it is difficult. And then I remember, you already have it. Just free yourself, reset your mindset, just forget about combining schemes. Because you don't need to combine them, you already have it. And you have to believe it strongly. And look at what you have. So let me show you how this miracle happens. So let's look at advection diffusion system. This is advection term and hyperbolic diffusion system. Okay. And in the steady state, we will get P equals Ux. Right? P will be is the gradient variable. So that means if Ux is P, we can do, this is what we can do. We can write advective term as A times P. And it looks like a source term. And if it is a source term, I can take it to the right-hand side. AP goes to the right, and S1 minus AP will be the new source term. So now the system looks like this. This is an advection diffusion system. But what does this look like? This is hyperbolic diffusion system. And do I have a scheme? Yes. I already have a scheme. I just described how to solve this using two characteristics at the face. and with source term. And any source term can go into that formula, and you can find U and P. So this is the active flux scheme for advection diffusion. So the flux has advective and diffusive fluxes. And then the cell average active, this is always conservative because it's defined by the conservative discretization of this whole system. And the question is how to compute this next time level flux fk plus 1. We solve diffusion with advection as a source term. So we have only one algorithm to compute the phase value. And for unsteady problems, we will have a physical time derivative, which is also a source term. It can be included into this source term, and exactly the same algorithm applies. So what I'm saying here is, okay, you can start with this finite volume discretization and how to compute flux. Usually, for advection diffusion or Navier-Stokes, we have a variety of choices for implicit fluxes. Implicit Riemann solvers, the flux vector spin, and then some combined with some kind of central viscous discretization. What I'm proposing here is let's use upwind scheme for viscous. For any of these techniques can apply to viscous. And then implicit term, just treat it as a source term. So this could be a new approach to Navier-Stokes flux. Yeah.
So the characteristics of the advection diffusion are exactly the same as characteristics of diffusion?
No.
Diffusion minus the source then, or
Not exactly the same. But it doesn't have to be. It's always like this.
Are they getting modified because you have advection as a source term now, or not?
It is not modified. This
Not
is just
modified.
diffusion.
Okay.
Yeah, this is exactly the same character.
So the characteristic would be the same as the diffusion?
Yes, symmetric.
So do you consider this one as truly upwinding? Because now the advection is no longer there.
No.
Because advection you treat it as a source term, so the
But I don't-
characteristic that comes from advection is no longer there.
No, but I don't see why.
No, I'm not saying it's bad, but I think the original idea of Active-Flux was to have truly upwinding scheme, and that is kind of compromise.
Yeah, you can do truly upwind in terms of this diffusion, which will be isotropic. And upwind for diffusion sounds
I know.
strange, but because hyperbolic diffusion describes isotropic wave. So when you do upwinding, you end up with a symmetric stencil. And I understand if this is an advective term, there's no upwinding there. I understand.
So that's treated as central? When you say you don't have any
I don't know how to call this.
You're an upward in the sense that you're tracing characteristics of the domain.
Yes, characteristic of diffusion.
Diffusion, not the advection.
Yeah.
That's fine.
Yes. So maybe I should look at like this community and see if it's going to work or not. Because for now, I have only smooth problems and focus on accuracy. So this is the final form for advection diffusion scheme. And to solve this globally coupled system over each physical time step, I use Newton's method. In a sense, active flux is a compact scheme. It depends on only the neighbor cells. But of course, it involves not just cell averages, but phase values. So it's not going to be a tri-diagonal system. To construct this Newton solver, I exactly linearize, which can be done in 1D at least. And I completely ignored the pseudo-time term and Gauss-seidel relaxation to reduce linear residual by 1 order. And typically, I apply this Newton integration to reduce the residual 6 orders magnitude for steady problems and 2 orders for unsteady problems. And let me show you some results and state So 1D advection diffusion with exact is manufactured solution, source type, with this boundary layer type exact solution. And I have 4 different grids, 16 to 128 cells. And A of nu is like a Peclet number or Reynolds number. It goes 0.01 to 100. So this is a diffusion dominant case, nu 0.01. Here is a solution. The black curve is the exact, and the circles are the cell averages, and the triangles are the phase values. And on the right, this is this should be P, the gradient computed by the advection diffusion scheme. And the error convergence, this is the error versus mesh spacing. The slope is 3 for all phase values and cell averages. And on the right, this is a Newton iteration. It takes only 5 iterations. But each Newton iteration involves Gauss-Seidel relaxation. And it takes 100 to 700 for final speed. But the increase, the number increases linearly. That's one of the advantages of solving hyperbolic system. For pure diffusion problem, this is quadratic. And 0.1, still diffusion dominates. This is just a little bit of effect of advection. But still, we keep stellar accuracy and 4 Newton iteration, and again, linear increase in the relaxation. And 1.0, now advection begins to affect the solution. And still, we keep stellar accuracy and same level of Newton iteration and relaxation. And 10, now we begin to see some boundary layer type profile. And then again, we still keep stellar accuracy and Newton iteration 4 or 5, and the linear increase in the relaxation time. So, and finally, this is a fully advective dominated case. There's a boundary layer on the right. And this is something strange I still don't understand. The order of accuracy for cell average for solution U is third order, but other quantities like phase values and the gradient are almost fourth order accurate in the advection limit, which I don't have explanation. And again, it's 5 Newton iteration and linear increase in the relaxation. And unsteady, there's an unsteady problem. I applied this third order scheme with BDF3, the third order BDF scheme. And this is the boundary condition is given at the left, solution is fixed, and on the right, solution changes in time. And this is an irregular mesh with 20 cells, and delta t 0.1 and final time is 6. And the exact solution is represented by red curve, and circles are the third order accurate cell averages. So this is a movie. This movie can be found in YouTube. If you search Active-Flux, you can find a couple of movies. And time accuracy, I use different time stepping and measure the error. And it is third order in time. And at some point, the time step becomes smaller, and the spatial error dominates. And for unsteady computations, typically 2 Newton iteration is required to reduce the residual by 2 orders. So, Active-Flux scheme constructed for unsteady advection diffusion. And the phase values are computed by solving advection diffusion as a diffusion plus source terms. And the Newton's method with 5 residual evaluations to reach steady state and 2 for unsteady. And we still don't understand this third order fourth order in the advection limit, which is a nice thing, but I just don't know why. So this is a very fundamental study, but we wanted to demonstrate that Active-Flux can be extended to diffusion and Navier-Stokes. And most of other efforts are focusing on Euler equations, nonlinear. And at some point, to solve turbulent flows, we need to extend this to diffusion. So this is one possible way to do it. So of course, we have to extend this to higher order dimensions, which can be done because the hyperbolic diffusion has a very simple structure like acoustic wave. But the biggest question is, can we extend it to Navier-Stokes? But you might expect by now, yes, you don't need to extend because you already have it. And you have to believe it and wait for NIA CFD Seminar on September 29th. I will talk about how this is possible. Thank you very much.